Welcome back. Today we're going to continue with our two-dimensional discussion, only instead of displacements, we're going to be looking at velocity vectors in 2 dimensions. Okay, so we're going to add 2 velocities, and you've done this in your life at some point, I'm sure, but you may not have ever stopped to think about it. So if you've ever tried to swim or paddle across a river, you've experienced the addition of 2 velocities. Okay, so if you're in a backyard pool with no moving water and you tried to swim straight across it and you picked a point on the other side, it would be easy for you to swim straight across to that point. Okay, you wouldn't have to do anything else differently. If you tried to swim across a rushing river, though, to a point exactly across from you, you probably had more difficulty and you probably ended up downstream because the water would wash you downstream. And that is the combination of 2 velocity vectors. So if you wanted to reach the point straight across from you, you would have to make an adjustment in your swimming so that your travel across the river would be a bit different. So let's have a look. This is what it would look like. Velocity of the current, velocity of the boat or swimmer, whatever it might be, crossing the river. And I've drawn them perpendicular to each other because that's where we'll start this conversation. And then we can see how we might adjust or adapt that depending on what we want to do. So we will do a couple of river crossing problems by swimmers or boaters, it doesn't really matter. We'll then move on to aircraft flying in air, and we'll talk about that type of problem. They're very similar, but again, you may not have thought about them in a physics way before. So just as a quick refresher, problems with no acceleration, okay, use the simple relationship v equals d over t. Okay, so that will be our primary equation for this section because we're going to keep the problems from a kinematic side very straightforward, and we'll worry more just about the vector pieces that we have to figure out. Okay, so let's try one. We have a river that is 0.3 kilometers wide, 300 meters wide. We have a school and a home in this one, and we are starting at school and we want to go straight home. Okay, we have a motorboat that can drive us across the river at a constant velocity of 12 kilometers an hour. The river is 0.3 kilometers across, has no current. Okay, that's important right now. How long will it take to cross the river? Well, if we look at this, this is basically one-dimensional motion. We have a velocity, we have a distance or displacement, and all we're trying to figure out is time. So our relationship that we just wrote down, v equals d over t, will be our guide. We have v, we have d, we're trying to solve for t. So if we pop over here, make sure our units are all in the right format. We're going to use kilometers and hours. So we rearrange our expression. We could multiply both sides by t, divide both sides by v, and we get a rearranged expression. And then all we have to do is divide 0.3 by 12, and we come up with the time it takes to cross the river. So 0.025 hours, which might sound like a long time, but as we did earlier this year, if we wanted to convert this, we would just times that by the 60 minutes in an hour, 0.025 times 60, and we would find it takes 1.5 minutes. Okay, so not particularly long to cross the river, 90 seconds. So there's our first case, and normally that one is pretty easy to follow. People can go, oh yeah, that makes sense. Okay, but now we're going to open the water up. We're going to go up to the dam and we're going to open the water. And we're going to let the water flow down the river. So let's do the exact same setup. We have a school, a home, motorboat can drive at 12 kilometers an hour. Okay, but the current now is going to pick up to be 24 kilometers an hour. And this is where your life experience and the physics will diverge. Because if you can imagine being in this situation, or if you've tried to swim across a river, it feels like you're going faster. And that word feels is a really dangerous because it doesn't necessarily change the math, but it might change the way you think about the problem. So if you look at this resultant right here, this VT, that is the resultant of adding the motorboat driving north and the current driving to the east, or washing you down to the east. So when you feel like you're going faster, the reality is you are. You are going faster. Your resultant velocity, because it's the hypotenuse, will be greater than both 12 and 24. The challenge, though, is you're also traveling on a different path. And that's the key piece. So if within this question, the only, out of the two components, the only piece that actually gets you across the river is this one. Okay, the current does not get you across the river any faster. It's traveling perpendicular to the direction you want to go. So Vy, or the motorboat pointed due north, is the only piece that gets you across the river. Okay, and that's a really tricky thought for some people. So we do this one the exact same way we did the first question. So even though the current is open, as long as my motorboat is pointed due north, I will incrementally, okay, and it might just be I move up a little bit and I get washed downstream. I move up a little bit, I get washed downstream. Something like that. Okay, whatever the pathway ends up being. But if you looked at all of these little vertical arrows, it would be equivalent to the first problem where we had no current. So it still takes me 90 seconds or 0.025 hours to cross the river. Okay, and that's tricky. Now, how far downstream? Well, once we know the time we're on the water, the time we're in the river, then we can take that time and multiply it with the vector that actually moves me downstream. So we could take our 24 kilometers an hour. Again, we're using our little expression v equals d over t. We know v, we now know t because that's the time to cross the river, so we can calculate dx, or the distance or displacement we are downriver. Okay, so we take our formula. Let's get rid of the whole thing here, and then I'll bring it up a little higher. Okay, so you can see we've rearranged the formula. We've multiplied 24 times 0.025, and we get 0.6 kilometers, or 600 meters downstream. Okay. All right. Now, if we were to look at the resultant vector, and this is kind of a fun one to do, and I apologize, this picture is not to scale, it's backwards. Okay, but we're going to just work with it anyways. So if we set up our two vectors, 12 kilometers an hour to the north and 24 kilometers an hour to the east. Okay, so they're over here, and again, this picture is not to scale. If we set this up and we do our Pythagorean theorem, that's this stage right here, we come up with 27 kilometers an hour. So we are traveling faster than just the motorboat by itself could normally travel. Okay. We can get the direction, again, just as we've done with our displacements. We take the 24 and the 12, we put that into tan, and we can get the direction that the boat is going to travel. Now, if you want to do an interesting little challenge here, the river, we said we were washed 600 meters down. We were, actually, let's maybe make it 0.6 kilometers instead. We said this was 0.3 kilometers. We could find that displacement by doing a quick Pythagorean theorem. Okay, so if we went 0.3 squared plus 0.6 squared, 0.6 squared plus 0.3 squared equals square root answer, and you get a displacement total of 0.67 kilometers. Okay, and you might be thinking, well, so what? Okay, well, here's why we're going to look at that real quickly, and you might be a little bit shocked by this. We're going to take this 27 kilometers an hour, so this displacement here was 0.67 kilometers. We're traveling at 27 kilometers an hour, and if we set up our expression v equals d over t, and we substitute in those values for that resultant, okay, and we solve for t, you ready? 0.67 divided by 27 equals 0.025 hours. Oh my goodness, that's the exact same time it takes to cross the river when we point the boat straight across with no current. Okay, so the time to cross is still the same. It's just a little bit to wrap your head around, so take a minute, pause, rewind, look at that again. It's a pretty cool idea though. Okay, so I'll pause it here. A swimmer swims perpendicular to the bank of a 20-meter wide river at a velocity of 1.3 meters per second. Suppose the river has a current of 2.7 meters per second to the west. So pause it here and try it. Okay, I'm going to draw my picture. Okay, so we're swimming perpendicular to the bank. It's 20 meters wide. The current is going to the west at 2.7 meters per second, and the swimmer can swim at 1.3 meters per second. So how long does it take the swimmer to reach the other side? Well, part A, our distance that we have to travel is 20 meters. Our velocity in that direction is 1.3 meters per second. So if we set up our little expression, v equals d over t, you have 1.3 equals 20 over t. T equals 20 divided by 1.3. And we should get 15.4 seconds. Okay, so that's the time it takes to go across. How far downstream does the swimmer land? Well, if we are in the water for 15.4 seconds, this vector here, that's the current, is going to wash us downstream. So we have a time of 15.4 seconds, a velocity of 2.7 meters per second to the west. So our distance would be those two multiplied together. So we would be 2.7 times 15.4 for 41.6 meters to the west. Okay, so let's have a quick look. How'd we do? 15 seconds and 42 meters. We're pretty darn close. The difference is just rounding. Okay, last part. Relative velocity notation. Okay, and depending on which textbook or articles you read, you might see different notation for this. So if we have a plane is flying at 500 kilometers an hour to the east relative to the air. So just like you're a swimmer and you swim in water, planes have to fly in a medium, and that medium is air. The air is traveling at 50 kilometers an hour to the east relative to the ground. Okay, the plane's velocity relative to the ground would look something like this. So you'll notice velocity of plane in air is 500. Velocity of air to ground, 500 or 50. Notice how these two guys here are both inside. Okay, and they need to be near each other. So this, when we combine them, the outside plane to ground ends up being here. Okay, so we end up with 550 kilometers an hour would be the relative speed of the plane relative to the ground. Okay, so now if we took that exact same problem, and what if the wind blew in the other direction? So now we have the plane is still trying to fly at 500 kilometers an hour in the air. But now our wind speed relative to the ground is no longer 50 in the same direction. It's 100 kilometers an hour in the opposite direction. So we're going to put a negative on that. So our velocity of our plane relative to the ground now becomes 400 kilometers an hour to the east. Okay, so we're traveling slower because the medium we're flying in is going quicker in the opposite direction. Now this is a crazy scenario. You would never experience this because you'd never put a plane up in the air. But what if the wind was traveling at 500 kilometers an hour to the west in the opposite direction of us? So we have our jets firing. We're trying at 500 kilometers an hour going to the east, and this wind is blowing at 500 kilometers an hour to the west. We would, be traveling at 0 kilometers an hour. Okay, so we would actually be hovering. So we would have to fire our jets in that 500 kilometer an hour wind just to stay in one spot. If we slowed down or dropped our jets down to 400, we'd actually travel backwards. The wind would blow us away. Pretty wild, eh? All right, so on page 75, 789, you'll find a couple of fun problems to try that are velocity related, as well as the one displacement one, I believe. And then there was also a relative velocities task for you to look at. And thanks for tuning in. Hope that didn't stretch your mind too far, but it's kind of fun to think about.